Hey guys, welcome to Safi Mixed. In this video you will learn how the shape of potential function affects the wave function of a quantum mechanical particle. Moreover, it will enable you to understand the concept of how to differentiate between bound and scattering states of a quantum mechanical particle. To this end, I consider a very general form of a one-dimensional potential and plot it against position coordinate. So I denote the horizontal axis with x and the vertical axis with Vx. Let the behavior of potential function is given by a curve like this one. We see that the value of Vx is not the same for all values of the position coordinate. This change in the behavior of potential results in different types of quantum states, which are the focus of this lecture. Let us denote the values of the potential in different regions by V1, V2, and V minimum, where V minimum is the lowest value of the potential on the curve, V1 is the maximum value to the left of the curve, and V2 is the maximum value to the right of the curve. It means that at x equal plus minus infinity, the potential has fixed values of V1 at x equal to minus infinity and V2 at x equals plus infinity. Since V is independent of time, therefore the solution to the Schrodinger wave equation for different choices of this potential are stationary state solutions. However, the solution could either represent bound states or scattering states of the particle. Let us understand the difference between these two types of states through the shape of this potential. If the total energy E of the particle is such that it is lesser than both V1 and V2 and greater than V minimum, the particle would reside in the region bounded between position x1 and x2 as shown in the plot. The solution of time-independent Schrodinger wave equation for such values of total energy of a particle are called bound states solutions. This means that the square modulus of the wave functions for such states in the specified region would always be 1, which ensures the existence of particle between position x1 and x2. These positions are in fact the classical turning points. On the other hand, if the particle energy is greater than V1 and lesser than V2, that is V1 is lesser than E and E is lesser than V2, under this condition, although the particle is not allowed to go to plus infinity, however, to the right, it is not bounded and can move to x equal to minus infinity. Similarly, for the particle with E greater than both V1 and V2, the particle can move to plus infinity and can move to minus infinity. In such cases, the solutions to the time-independent Schrodinger equations are called scattering states. So a solution to the time-independent Schrodinger equation that allows a particle to move either to plus infinity or to minus infinity or to both at the left and right side is called a scattering solution. On the other hand, a solution that limit the moment of the particle to both plus and minus infinity and keep the particle within a limited region is called a bound state solution to the Schrodinger wave equation. Now you must note this: for the bound state to exist, the potential must at least have one minimum whose value is lesser than one of its asymptotic values. In the present case, the asymptotic values are V1, which is the value to the left at minus infinity, and V2, which is the value at the right to plus infinity. Furthermore, in bound state, the energy spectrum of a particle is discrete, whereas in the scattering states, the energy spectrum of the particle is continuous. So, on the plot, I have represented bound state, curve region of the potential, and the continuum state in the free region of the particle, where the energy is greater than at least V1 at the left asymptote. And video part 2 on bound states, I discuss and provide proofs to 3 very important properties of bound states. So stay tuned and don't miss part 2 of my videos on bound state.